Mojtaba, and I'm glad that I'm here to present my work that I've done with FreeFEM. My presentation is focused on a software that we have developed using FreeFEM. We call it BioDeg, and it's a simulation software for biomaterials degradation simulation based on FreeFEM, PETSI, and Qt. So I will present a little bit of the modeling work that we have done, but I will focus more on the things that this software has for the for the FreeFEM community and the things that it might be useful in that case. So yeah, I will present both sides. So I start with a very general overview of the software. The software is a multifunctional 3D simulation code for corrosion simulation, for corrosion modeling, and it has features a cross-platform user interface that apparently is developed by Qt, using Qt, and included the pre and post processors, and they are also mostly done in FreeFEM. And so generally it's a FreeFEM backend. So the main code, the core of the model is developed in FreeFEM, and the front end is in Qt. And this is fully available as an open source software. So a little bit of the basic concepts and the background of the tool. So talking about biodegradation, especially for the metals, we are talking about magnesium, zinc, and iron. And we mean that the material that you put inside the body and they gradually disappear and get absorbed by the body and get replaced by new bones and tissue. And they're getting more popular and gaining more attention because they have great mechanical properties and also positive contribution to biological aspects of the body. But still the problem is the release profile, the way that the speed, the rate of the biodegradation and the way that the materials released to the body should be tuned and should be adapted to the specific application based on various applications that they might have. So the basic question that this research is trying to address is actually tuning the biodegradation properties to the regeneration of the new bones in tissue engineering, let's say, in biomedical engineering, and also trying to optimize the implant design based on the release profile, so everything virtually. That was what we were trying to address, and we solved it by a mathematical model of the core biodegradation, the chemistry biodegradation, and coupling these things with models like with tissue growth models and cell growth models in this kind of stuff, while we consider the environmental effects as well. So the concepts, let's say the quantity, the entities that we used for the modeling workflow is for underlying sciences, mathematical models, and computational models, consists of the chemistry of biodegradation. This is what I will talk about in this presentation, but also the physics of perfusion, which is actually fluid flow for various kinds of bioreactors that we usually use in experimental setups, and also the biology of tissue growth. But for mathematical models, we model these things using a set of partial differential equations that are reaction, diffusion, convection, as well as Navier-Stokes for fluid flow, and level set and phase field for tracking the interface. I will describe it later. And for computational models, it's a combination of finite element method and finite difference, and parallel computing libraries and open source solvers. So the chemistry of biodegradation is actually, in the basic point of view, is the solution of metallic implants, releasing ions, and then formation of side corrosion products, and also effects of the environment on this film of these side products, and also the rate of degradation, as well as change in various chemical components or chemical entities like pH. The way that the mathematical representation works to convert this chemistry to mathematics is, for example, this is a very basic reaction, but then we can have the concentration of different components expressed as functions of space and time, and then we can derive, something like this. Of course, as I said, this is a simplified version, But then this is a kind of system that we have for modeling the chemistry over time. So this system can capture the essential things that I mentioned. And by solving this, we can have the mass transfer phenomenon that is occurring during biodegradation. But it's also important because we want to study how these materials, how the medical implants will evolve inside the body. So we need to track the change of morphology, let's say. And for doing that, we use an implicit formulation of the interface. This is a crucial part of the work. And we use a level set formulation for that. We could have also used phase field. We use it for another purpose, but I don't present it here. So for the biodegradation, we use level set, correlating the speed of the velocity to the change of the concentration of materials, and then formulating the level set method to something like this based on the release profile. So this is, for example, this can be the 5th PD that we need to solve. And from the implementation perspective, it is like, yeah, generally the level set method that is, for example, 0 on the interface, negative outside and positive inside. So generally this is an Eulerian mesh that we just label different parts of the domain with different labels. And then by solving the level set method, we can track how it evolves over time. For implementing the computational model, for constructing, as I said, we use a combination of finite difference for which is actually used for temporal derivatives and finite element for spatial derivatives. I don't go to the details of this because this is quite standard, although there are some tricks that we have used from the HPC perspective. But yeah, as I said, I want to focus more on the software aspect. So, but this is quite general and standard. And the important thing is the mesh should be refined to increase the numerical accuracy on the on the moving interface, on the boundary, let's say, moving boundary problem. So this is an Eulerian mesh, as I said, and we refine the mesh on the interface as it moves. And in order to implement it, yeah, for mesh generation, I've used Salumi and MMG. A typical simulation contains usually 10 to 20 million of elements. And for weak formulation in FreeFEM, the degrees of freedom for each PDE will be 2 million to 4 million. And we have 5 PDEs excluding Navier-Stokes. So parallelization will be essential. And for parallelization, we have used HPDDM, the great work by Pierre, and also the nice interface to the rich library PETSI inside FreeFEM for preconditioning, and also the Parallel.io using ParaView. And for level set implementation, this is the bottleneck of the model. That is, we need penalization techniques on the interface for the interface boundary conditions, because the boundary conditions of the system are applied on the moving interface. So the boundary conditions are applied on a solution of one of the PDEs, and we use penalization technique to impose them. And then for dealing with concentration oscillations that are occurring on the interface, we use mass lumping, still available in FreeFEM. And then for computing the gradients that is required for the level set formulation that we have done, it's quite tricky in FreeFEM to be done. So we use a technique like this, that we compute at a constant value edge. And instead of computing the gradient exactly on the interface, we move a little bit forward to the Floyd domain, and we compute the gradients there. And by doing this, we are able to compute the gradients and ignoring the oscillations. And then problem of redistancing, because we need to redistance the distance function of the level set every now and then. And especially when it is in parallel and it meshes decompose, it becomes a little bit tricky, but still that is something manageable. But this is actually one of the problems that we had generally in this work, because for the interpolator that is available, the powerful interpolator inside FreeFEM, yeah, it sometimes causes some problem for us because we are very sensitive to the interface. The interface is a measure for us for mass loss, and sometimes by a small change in the interpolation, that the way that the FreeFEM interpolates functions, we will have some jumps in the mass loss that is not really good for us and appropriate for this implementation. And then if we want to consider convection, it is adding fluid flow and for being able to simulate hydrodynamics conditions requires dealing with Navier-Stokes equation. And for doing that, we have also implemented parallel fluid flow code. This is also freely available in a repository on GitHub. And this has been a source of also a couple of discussions in the community of FreeFEM regarding the schemes that I have used or preconditioners. And I'm really happy that yeah, we had that discussions also on the community with peer and also other people on this. And then one important aspect of this is I've compared it with, for example, other CFD codes like OpenFOAM to be sure that this code, the CFD part produces the results that are valid from the numerical perspective as well. So for parallelizing computations, it is, yeah, as I said, we have used HPDDM for distributing the mesh among the available resources. So we've used the technique overlapping Schwartz method available in HPDDM, and it works very nice for our case. And also solving for the solution of the linear system, we use a set of different preconditioners. I will show you the results later, using the Boomer AMG for the reaction diffusion system and field split for fluid flow, and also iterative solvers. So a set of results just to show that what I was talking about. So this is you know, typical results that we have, for example, for the degradation of orthopedics implants, orthopedic screws. On the left, you can see the release of material, and on the right, that's actually the zero ISO contour of the level set function, showing the change of the geometry of the implant over time. This is for porous scaffolds widely used in tissue engineering. You can see on the left, it's the formation of the protective film, as I said, the corrosion products on the interface. And on the right, it is the release profile and the way that the morphology, the shape of the implant changes over time. This is for jaw bone plates, the bone plates that people, yeah, the surgeons use in mandible. And this is actually the simulation over a larger time period. I'm using it further to also construct some mechanical analysis simulations. And this is a simulation for narrow cuboid rendered using a GPU, showing how a narrow cube would disappear. This was used actually for validation of the models using numerical, using quantitative results. This is, for example, the change of one of the quantities that is important for us, the pH, that can be used to validate the models as well, to compare it with the experimental setups we have done in different diffusion regimes, which means with different solutions, like it is a saline solution, high diffusion, and buffered solution, low diffusion. And the results are really in good agreement with the experimental results, as you can see here. So this is actually, this has been already published with this kind of quantitative analysis out of the numerical values. And also for the things that I said for comparing results with OpenFOAM, this is a test case that resembles the experimental setup, inlet and outlet. And you know, we've compared it from different aspects, and they were exactly in line with each other. Also from the quantitative perspective, this is, you know, a very general overview, but the only difference that I saw was on the boundary value formulation, because yeah, OpenFOAM is quite good at that. There was some differences on the boundary of the domain, but except from that, everything was exactly in line with the simple foam solver of OpenFOAM. And this is what happens if you have the flow to the degradation. It is in 2D. That is when we have a flow from left to right, you can see that the effect of convection, and also it can be like a directional degradation. And also a little bit of the parallel strong scaling things. This is also published in full analysis of what we've done for the parallelization for the schemes, because I said there are some tricky parts here. So this is a strong scaling, also weak scaling. Weak scaling results are not here, computing the parallel efficiency and speed up to a problem that is not very big, 1 million elements more or less, and then trying to compute this, the parallel efficiency and the portion of the code that can run in parallel and this kind of stuff. So this has been also investigated deeply for this model. And another thing that we've done is taking, trying to use different kind of preconditioners and solvers to solve the system for a limited number of PDs. As you can see here, just 3 PDs. Yeah, comparing the performance of different the combination of preconditioner and solvers and choosing the best one, and also reporting that, yeah, we got best results using, for example, here, as I said, Boomer AMG from Hipre and also GMRES iterative solver. And for the software development, as I said, this is an interface on a FreeFEM code. So this is the output of a FreeFEM code, for example. But then we've developed a cross-platform, customizable and adaptive user interface on top of this. So it reads actually the output of the terminal output of the program and tries to visualize it for the user. And at the same time, it's also possible for the user to configure the simulations from different aspects. So for example, different options. So all the parameters of the simulations are written in a way that they can be configured from a command line argument, like parameters. And then, yeah, just passing the parameters to the simulation code and reading back the terminal output and trying to monitor the written output files, VTK files. So generally, this can be like a template for any other, if it is any other one interested in developing such an interface on top of FreeFEM code. This can be a template that anyone can use to quickly build up interfaces, let's say modern interfaces on top of FreeFEM codes. And it's quite possible and quite straightforward. I can say that my experience says that it is quite straightforward and without any difficulty. And also general preprocessor has been developed using ParMMG to embed a mesh inside a container, because as you've seen, it's an Eulerian mesh. So we need to embed a part like a scaffold or something inside another container that is actually the solution and an environment. And this tool can be used to generate such stuff, and also mesh refinement on an interface, as I said, using the great tool ParMMG, and also the integration of ParMMG inside FreeFEM. So this is an example that we have this kind of, for example, gyroid structures, gyroid, let's say, scaffolds, and then by using the tool, of course, this is not a great, yeah, the initial mesh was not very refined, was not fine enough, I can say, but this is the kind of output of the preprocessor that generates this kind of mesh actually for the simulation. And for the post-processor, it's developed using Python and QChart, and it is now basically integrated into the UI. But in the future, I should definitely consider embedding like this kind of portable ParaView components like ParaView glance into the user interface. So it will be much easier for users to be able to post-process the simulation results. And also a couple of final words on open source and open science. So as I said, all these tools are available as open source code, although this is still an ongoing project. But so I'm still doing lots of development on the repositories, but they are all, yeah, if someone want to use this as a template for building the UI, or generally is interested to see what are the numerical techniques that we have employed, the codes are available on GitHub for the core models, for the user interface, and the preprocessor using ParMMG, as I said, and also for all the documentations. And also, as a final note, I'm interested to say this because this can be relevant to the FreeFEM community, that we've started a YouTube project to share experiences on open source tools. But you know, the kind of simulations and things that I'm usually discussing on this project are 99% done using FreeFEM. So yeah, I want to describe like how we've constructed these models, how we post-process this stuff, but generally, you know, as I said, more than 90% of times I'm talking about FreeFEM. So this is something that can have also contribution from the open source community if anyone is interested. But yeah, this is I'm proud that I can promote the usage of FreeFEM, because yeah, I was quite satisfied with all the tools and libraries that is available actually via FreeFEM for my PhD. So yeah, I am really grateful to the community and to the team of developers of FreeFEM. So thank you so much for your attention.
Thank you. We have time for a question. Maybe.
I have a question.
Oh.
Do you hear me?
Yeah, yeah.
I think you focused nicely on the fact that you're using open source software. So Linux, for example, how do you think it would be to port this, for example, to Windows, which has Qt also available?
Oh, sorry, Pierre. I'm really not able to hear you clearly. You know, the main parts I cannot exactly understand what you are saying.
Better now? Is it better?
Yeah, yeah. Now it's clear. Yeah, yeah. Sorry.
You focused on the use of open source and
yeah,
and Linux, for example. How difficult will it be to apply this work, for example, to Windows, which also has Qt available, but which is a little bit harder to program on, let's say?
Yeah. No, but you know, because you know, I intend